Okay, so I think I'll. Can you guys hear me?
Yes, sir.
Hello. Yes. Okay.
Yes,
So
sir.
we will start with the. We'll continue with the discussion that we had in the last class. That is how to see Poisson process as a limit of binomial. Right. Okay. Let's look at that. So Poisson as a limit
Screen
of.
is not good.
Oh yeah, yeah. Sorry, I completely forgot to share. Okay. Just sorry. There's some. Yeah. Okay. Can you see?
Yes, sir.
Okay. Binomial. Okay. So this is what we are going to look at. So essentially, what we will do is the following. Okay. So let's say I'm going to divide the time into smaller intervals. Okay. This is your time axis, and I'm going to divide this into smaller intervals. Okay, so let's say 1, 2, 3, and so on n. So think of this as a division of 0 to t interval into n small pieces. Okay, now let's forget about the time axis t and only focus on this n, 1 to n. Okay, in each one of them, let's suppose that there is an arrival with probability p, or there is no arrival with probability 1 minus p, and it's independent across slots. Okay, is that fine? So that means in n slots, what is the average number of arrivals? Can somebody tell me? So each person will toss a coin. If it is head, is going to go there. I mean, in the slot I. Otherwise, he is going to back off. In slot I plus one, somebody else will do the same thing. Okay. What will be the average number of arrivals in the n slots?
NP, sir.
NP. Right. Good. So the average arrival would be, I'll call it as lambda. Okay. So is NP. Okay. What I'm going to do is, of course, as the heading says, Poisson as a limit. So I'm going to take some limit. So I'll take n tending to infinity, but I'll ensure that this Pn, okay, nPn, right? So this product tends to lambda. Okay, so let me put it this way. So this npn, as n goes to infinity, I'll ensure that this goes to a number lambda. So this is the average number of arrivals in 0 to t seconds. Is that fine? Okay.
Sir,
So
why
now,
P in, sir? Because we have taken the probability P for the all
oh, no,
for
no. So
every.
as n changes, I'll change my probability of head to occur as well. I'll pick a different coin.
Okay.
Okay, so what I'm trying to do here is I'm going to divide this time axis into n, but I want to make it finer and finer so that in the limit it's continuous, right? This is discrete now. I have to go for a Poisson process. So Poisson is continuous time, right? Arrival can happen at any time. Here in binomial, the arrival can happen at only discrete time intervals or in slots. Do you agree?
Yes, sir.
Okay. So now, what is the probability that there are k arrivals? What is the probability? Can somebody tell me? Yes?
NCK.
Huh?
N choose K.
How do you n choose k? N choose k as n goes to infinity, it will be infinity. So probability, you are saying infinity.
No, sir. Yeah, into
Binomial PMF, yeah.
binomial.
Yeah. So what is that? Sumit, can you tell me? It's like k heads in n
Yes, sir.
tosses, right?
NCK
N choose k,
P to the power K 1 minus P to the power N
n
minus K.
minus k. Good. Right. So of course, k is less than or equal to n. Okay. So if I say k equal to n, then it's essentially p power n. right? That's the probability. Okay, now I have to take the limit. Okay, so this will be, I'll call it as Pn, okay, because I'm going to take Pn also to infinity. So now as n goes to infinity, I have to see what happens to this. N choose k, p power k, 1 minus p power n minus k. Okay, so this is same as limit. I'm going to write the entire thing in terms of n and lambda. Okay, so what is Pn? It's lambda by
Lambda
n.
by n.
Okay, at least in the limit, that's what is going to happen. Okay, so lambda by n whole power k. Okay, 1 minus p is what? Lambda by n whole power n minus k. So yeah, so let me write it as is. Okay, fine. Now I can write. So what I'm going to do is I'm going to write it in a different color. So I'll just write this, okay, without the limit. Let's see what happens. See, the first one is n minus, n choose k is n factorial divided by n minus k factorial into k factorial, right? It's lambda power k or n power k, right? Into 1 minus lambda by n power n, right? Whole power minus k. Do you agree? Oh, sorry, I'm sorry. This is, I should write it as n into, I can write it as 1 minus k by n. Okay, fine. Okay, so this is what we have. So now I can just take, for example, lambda power k and k factorial out. So I'll just take lambda power k or k factorial out. Okay, and then I'll write the remaining. So n factorial divided by n minus k factorial into n power k. I have 1 minus lambda by n into, okay, I'll just write it as n by k. Okay, now what can you say about this as n goes to infinity? Yes.
Sir, if we
What
go
happens
to
to
the
this?
previous step, it will be e to the power minus lambda k in the previous step. How you wrote?
Which one?
Sir, yes, sir, the last step. If we take n tends to infinity, it will be the limit goes e to the power minus lambda k.
So this, as see, it's of the form 1 minus x
Yes,
whole
yes.
power or 1 minus 1 by x whole power x, right? That's the form. In fact, there is a there, right? So if you take x go into infinity, what happens to this? This goes to e to the power minus a,
Minus
right? So e to the power minus lambda.
lambda.
Okay. Now we have e to the power minus lambda factor, lambda power k or k factorial into this. So what can you say about this? Yes, sir. Question.
Sir, here we have to the power of n minus k, no, sir?
Correct.
But what 1 minus a by x whole power x, that goes to e to the power of
No, it's
minus
power n. I'm talking about power n. K is fixed, right?
Yes, sir.
Right. So this goes to e power minus lambda. Do you agree? Okay.
Sir, if we split that one, then we can get it directly, sir.
Which one? If you split
So
what?
n minus k is there, no, sir? So if you can write 1 minus lambda by n to the power n into 1 minus lambda by n to the power
So
minus k.
essentially,
So
it's like 1 minus
ultimately, it will
lambda
be,
by n power n divided by 1 minus lambda by n whole power k.
yes,
As n goes to infinity, lambda by n goes to 0. So 1 minus
yes,
lambda by n goes to 1. 1 power k is 1. So the denominator will be 1. The numerator will be my e power minus lambda. Okay.
yes, sir.
So what happens to this? N factorial, I can split this into what? N minus k factorial, right? Into n minus k plus 1 and so on till n. Okay, do you agree? So this and n minus k factorial cancels, and what we have is n minus k plus 1 into n minus k plus 2 and so on till n divided by n power k. So this goes to 1.
One,
Is this clear?
Yeah.
This is clear, right? You can check that. This is simple ratio. So this implies what? Limit n going to infinity, of course, such that Pn times n goes to lambda. Probability of k arrivals is e power minus lambda, lambda power k over k factorial. This is Poisson. Okay. Now, if you look at this, we haven't taken time into account, right? So, what is it that I'm doing? I'm doing, splitting t into, let's assume that each size is delta. So I'm going to divide t delta into n times is t. Okay, so delta times n is t, right? Or n is t by delta. Okay, so what will be Pn times n? So Pn t divided by delta is lambda, or tends to lambda as delta goes to 0. So what do you mean by n tending to infinity? If n this goes to infinity, delta goes to 0, so that the rate at which both go to respectively infinity and 0 is such that the product goes to t. Okay, that's how I'm going to take the limit. So now if you substitute this, what you end up getting is the same thing will be e power minus lambda t. That is the number of arrivals per second times t is the total number of arrivals in t time slots. Lambda t power k. So that's what we get, k arrivals over k factorial. So this will be your Poisson. Okay, this is homework. You have to check this. Okay, fine. So there is an alternative way of constructing Poisson process. You can just construct Poisson process by constructing a binomial process and take the limit. So that's another way of looking at Poisson. Okay. So let's look at the few things that I mentioned in the last class. Splitting and combining, right? So what happens if you combine two Poisson process? What happens if you split? Okay, so I will do one of them. So combining is easy. You have two Poisson process. You add the two Poisson random variables. You should show that the respective thing is a Poisson process. Okay, so I'll just write that as a result. I won't prove it. It's almost simple. Okay, so let x1 be Poisson with rate lambda 1 and x2 be Poisson with rate lambda 2. Okay, both lambda 1 lambda 2 positive, independent. Okay, both are independent. Okay, then if you take the sum, right, so let me call this as y, which is x1 plus x2 is again Poisson. It's Poisson with rate lambda 1 plus lambda 2. Okay, this is the first result. What is the second result? This is what I'm going to do. Okay. Okay, I won't formally write the result. I mean, you can do it. So I'll write it as a picture. Okay. So I have rate lambda. Okay. There is an arrival rate lambda. I'm going to split this into two streams, P and 1 minus P. How am I going to do that? Well, there is a car arriving. I'm going to toss a coin. If it is head, I'm going to ask the car to go to the left, otherwise to the right. And I'm going to keep doing that in an independent fashion, because the tossing of a coin experiment results in IID outcomes, right? So now this has some two streams. Now the question is, what happens to this? Is this, what is the rate here? And what is the rate here? And what will be the distributions, right? That's the question that we'll ask. Okay, so here, for example, n of t, the number of arrivals in t seconds. So this p n of t of k is basically e power minus lambda t power k or k factors Poisson. Is this clear, everyone? Hello?
Yes.
Yes, sir.
Let me call this as n1 of t and this as n2 of t, just the notation. Okay. Now I want to find the joint distribution, or I want to find what is n1 of t and what is n2 of t. Okay, so let's find a joint distribution, and so that the joint distribution of this is the product distribution. That means they are independent, and not only that, each product, each expression on the product corresponds to a Poisson arrival. Okay, so let's look at this. So I want to ask this question, right? So what is the probability that n1 of t is, let's say, some k or m, and n2 of t equal to k, given n of t is equal to n? That means I have n here, and I'm going to split this into 2. Okay, is that fine? Fine, right, everyone?
Sir, nt is the sum of the n1 plus n2,
Yeah.
sir.
So basically, this is m plus k. Okay, is that fine? Okay.
Yes.
Now let's see why this is true. So okay. Now how do I find this? What do I do? What do I do? What is the first step? What do you think is the first step?
So conditional probability definition.
Yes. What is that?
It's probability of n1t m comma n2 t.
No, that's correct. But what can you say about this n1 of t into n and n2 of t?
Sir, n1 and n2 are the Poissons processes.
They are independent.
They are independent. That's correct. No, n1 and n2 need not be independent, right? So why do you say that they are independent?
No, sir. N1 and N and N2 and N.
Not really, right? So if you look at the joint distribution, what do you think is the so how do you find this? That's the
So
question,
we
right?
can write into like k in terms of n minus m, and then expand this conditional probability. And then, so I mean n1t equal to m and n2t equal to k. We can write k in terms of n minus m,
Okay,
and then expand
okay.
it.
So k is well, n minus k is m, right? Sorry, n minus m is k, right? So that's what we have here. So that's the notation that we have used. So now, if I split, okay, so let's look at individual only. Okay, so what will be the distribution of individual? So before this, let's see what will be the distribution of n1 of t equal to m. Let's see what will be the distribution. What do you think is the distribution?
Sir, here rate will be, I think, sir, lambda p. I
So
think,
this
sir.
I can write the probability that n1 of t is m, okay, given n of t equal to n into probability of n of t equal to n. You are saying something overall n equal to 0 to infinity, right? Okay, so in fact, if I cannot just go from 0, because that will be this first probability will be 0, at least you should start with m. Yes, Sumit, you are saying something.
No, sir, I didn't get these lines actually. How can we write the summation form, sir? Because it is given particularly the n1 is equal to m. So we are asking.
I'm just this is the total probability law, right? Probability of A is probability of A given Bi into probability of Bi over all I. That kind of a
Yes,
thing,
yes.
right? Yeah. So now, what can you say about if I say n of t equal to n? What is the probability that n1 of t equal to m? Okay. Okay. So maybe okay. So let's look at this itself. So what do you think this is? So maybe this is something that you know. Okay. So if I can answer this, I can also answer the original, right? Suppose I have n. Okay. So this is the picture. So you have this comes into a box, gets split into 2, right? Okay. What I'm looking at is, okay, in goes n, out comes m and k. So I'm asking what is the probability that this will be m and this will be k. given that whatever is coming in till time t is n. So when will you push this each packet coming here to here? When will you push?
When there is a head.
When there is a head, right? So whenever there is a head, you will push there. So how many times are you going to toss the coin?
So NCM into.
Hmm?
So from n we are having m.
Sir, we
head,
need to get
NCM.
M heads in tosses.
Exactly, right? M heads in n tosses, right?
NCM.
M heads in n tosses and K tiles in n tosses. That's what you need to get. Do you agree? Okay. So this is nothing but, and what is the probability here? This probability would be, so you should get m, right? So p to the m, 1 minus p to the power k, right? That's what you have. So this is nothing but binomial, right? So it's, what is this? This is, I can write this as n factorial. N factorial is nothing but m plus k factorial divided by m factorial, that is m plus k minus k factorial into k factorial, right? This is m plus k choose m, right? That's what you have. P power m, 1 minus p power n minus, this is n minus m, which is k. Is this fine? Okay with all of you are okay with this?
Yes, sir.
Huh? Do
Yes,
you
sir.
agree? Okay. Now I have this. So, but if you look at this
Hello,
joint distribution, yes.
sir. I mean, at the junction point, we assume there is a. I mean, we assume that P, right? We didn't have any prior
Yeah,
knowledge of P.
yeah, no, we do have prior knowledge of P. I have designed the coin.
Okay, okay, yeah.
Okay, that's the assumption. Okay, so now this is equal to that binomial. So, but this is a conditional probability, right? This is nothing but probability of a comma b divided by probability of b, right? So this is n1 of t equal to m, n2 of t equal to k, n of t equal to n. That is implied from this, so we need not write that. Divided by probability of n of t is equal to n. Okay. So now, what is it that I'll do? I'll find this by multiplying this to this. Okay, so this implies joint distribution. That is probability of n1 of t equal to m, n2 of t equal to k is this whole thing, right? M plus k factorial p power m 1 minus p power k divided by m factorial k factorial times p of n of t equal to n is what? E power minus lambda t power n over n factorial. So n factorial and m plus k factorial cancels. Okay, is that fine? Fine, right?
Yes, sir.
Okay. Now, how do I write this? I can just do some rearrangement. I'll write it here. Okay. Now, the first thing that I do is I'll write p power m. Okay. P power m. Fine. Divided by m factorial. Okay. Is that fine? Okay. Now I'll write this as e power minus lambda t. Okay. We have it here. So the remaining I'll write it here. 1 minus p power k. Okay. By k factorial. Unfortunately, okay. So now what can you say about this term now? Huh? What can you say about this term? Yes. Hello. Hello.
Sir, lambda Tn is also there, sir.
Huh?
Lambda T to
So
the power n is also there.
t power m, there'll be lambda t power. Did I miss something?
So n equal to m plus k, so we can lambda t to the
Yeah,
power
so
n.
lambda t. Okay, so you are right. Sorry, this is what you are saying, right? Okay.
Yes, sir. Yeah.
So now I can also have lambda t power k here. Okay. Now, what can you say about this? I cannot say anything unless I put p here. Now, what can I say?
So Poisson with the parameter lambda p.
Yes, right? Okay. If I have to get this, so well, remember, I have inserted p here. Okay. So what I will do is I will insert 1 minus p here. So if you take the product of these two, you will get e power minus lambda t. Do you agree? This is convex combination. Okay. So what can you say about this? This is Poisson with rate
1 minus p lambda. Sorry,
1 minus p times lambda, right? This is because I can multiply these two. And similarly, this one is Poisson with
lambda
p
p.
lambda, right? So that means these two are independent because joint distribution is equal to product. Each one has Poisson, so we have the answer, right? If you split, it becomes Poisson. If you combine, again, it becomes Poisson. Is that fine? And you can generalize this to not just two. For example, if you have a road or a router with 100 incoming routes, each arriving with certain Poisson, and if you combine them, the result will also be Poisson. If you have a router, you are sending packets out in 100 routes, then each one will have again Poisson. Okay, so of course you have to use a coin to split. Otherwise, it's not true. But otherwise, yeah. Is this fine?
Hello, sir.
Yes.
Sir, Poisson was a continuous process, right?
Yes.
And then we bring the notion of like tossing a coin or whatever, that it's kind of I mean the output, is it kind of discretized because
no, what is so the numbers, the number of packets, that is always discrete. Okay, but the time or instant at which it arrives, for example, even if you when you split, right? So if you look at the time instant at which the packets are arriving here, again it will be exponential with rate lambda p, and lambda times 1 minus p for the other route. Okay.
yes, sir.
Okay, is this fine? Okay. Okay, so yeah, so you can generalize this, take that as a homework. Okay, so you can use induction to generalize. Okay, so there's one more thing that I would like to mention. So it's about the queue. So there is something called the notation that people use. Okay, so what is the queue? So essentially people write it like this, and you have incoming, and there is some service. Okay, so what is a queue? So you have a counter, people are coming to the counter. So, and the person sitting inside the counter will serve the request. As soon as he serves, that person will leave the counter. Okay, so how do you describe this process? The first thing is you have to describe how people are arriving, the arrival process, right? And the second thing that you need to describe is how the person is serving the request, right? That will also determine how long the person will be there at the counter, right? That is called the service. And the third one is the departure, right? So how he is going to sorry, the third one is how many counters are there, right? Maybe the queue could be one, but there are 4 counters, right? So I need to describe that. Well, you know, generally the way people describe these kind of things is through what is known as the bar notation. So I'll write this as G comma G comma N. Okay. So what does this describes arrival? Okay. This describes service and describes number of counters. Okay. Counters or yeah. Okay.
The counters are in series or parallel?
Counters or servers.
Sir,
It doesn't matter, right? So if there is one queue and there are 3 counters, what do you do?
Sir, I mean one after another, like that.
Exactly. So whichever counter gets empty first, the immediate person will go there, right? It's almost like, I don't know if you have in airport you check in, right? So you are in one queue and there are multiple counters. Exact same thing. Okay. So an example of this is called MM1Q. Okay, this M stands for what? Memoryless. Okay, that means arrival is inter-arrival times or memoryless property. It has memoryless property. Similarly, the departure is also memoryless. Okay, think of Poisson arrival with rate lambda 1 and Poisson departure or a service rate with the Poisson service with the rate lambda 2, and there is only one server. Okay, if I, for example, if I say MG1, that means the arrival is memoryless, the departure is general, it could be anything, and there is one server. There is another way of writing this, MD1, DD1, okay, so I'll tell D is deterministic, okay, D, M1, and so on, okay, D is deterministic. That means, for example, periodic, every 10-second people are arriving at the queue. And the service, every 2 seconds he is serving the person. So that is deterministic. Is that fine? This is something that people use in the in queuing theory literature, which is worth remembering. You will encounter these kind of notations once. Whenever you encounter, this is useful. Is this okay?
So what is G?
G is general. Okay, general meaning not memoryless, basically. Not memoryless, not deterministic. For example, non-homogeneous, so correlated arrivals, okay? So 3 of your friends go to a movie theater, that's correlated, right? Right? The arrival is not independent, it's not memoryless, right? Do you agree?
So will you please explain once more?
So what do you mean by correlated arrivals?
So I mean, my arrival is also my friend's arrival depends on me. Something like that.
Correct. Yeah. So because you are going to the movie theater, I also go, or your friend also will go there, right? So that means the number of arrivals is also correlated. Because you go, somebody else is going. And not only that, the time instant at which you are going. See, if you say that I'm going to go for a movie at 4 p.m., then that person will also go at the same time, right? The arrival instants are also correlated, right? So it's not a memoryless property, right? And for example, if the movie turned out to be very good, then you repeat. For example, you go the next day, then you are remembering the fact that you went yesterday and the movie was good and you're going again, right? So, do you agree?
Yes, sir.
So it's not independent increment and memoryless process. It's a highly correlated process. In fact, with burst arrival, because you are very popular and you go, therefore 10 of your friends also go to the movie, right? That's a burst arrival. Okay, is this fine?
Yes, sir.
Okay, so I think in this chapter there are a few other things. For example, conditional arrival densities and order statistics, which I will skip. If required, you can come back and refer to that particular section. Okay, so now we will go to the next chapter, which is about Gaussian random vectors and processes. So this is something very, very important. Okay, Gaussian random vector and processes. Okay, is this fine? Did I? Oh, I'm sorry. Okay. Okay, so now if I say, for example, W is Gaussian, okay, with mean 0 and variance 1. What does that mean? That means the density function. Can somebody tell me what is the density function of this?
So 1 over root 2 pi
Root 2 pi e power minus
exponential
x square by 2. This is for all x in
X.
R. All right. This is the notation. So this is the density function. Okay. Is that fine? Okay. Now suppose I scale this. Okay. So I get y, which is some let's say some sigma times x or w. So what do you think will be y w? So what do you think is the distribution of y? So how do you find this? I'll just quickly go over. You need to find the CDF first, right? What is the CDF? Its probability of sigma W is, of course, sigma is positive. Okay, so this is greater than 0. This is sigma W is less than or equal to Y, or W is less than or equal to
Y by
Y by.
sigma.
This will be your CDF of, this is nothing but CDF of W with Y by sigma, right? And if you take the derivative, what do you get?
PDF of W.
What will be the PDF of this thing? It will be same as PDF of W, but you have to scale Y by sigma, right? It's 1 by sigma, the density of W, but you scale it by sigma, right? This is the density, right? If I take the derivative of some function of Y by sigma, it's 1 by sigma times the derivative of that function of Y by sigma. What is this? This is 1 by root 2 pi. I have a sigma here, I'll put it here. E to the power minus x squared becomes what? This is y by sigma. So this is y squared by 2. Y by sigma becomes y squared by sigma squared. Right? So what is y? You can say y is Gaussian, 0 mean variance sigma squared. Okay, you know that sigma squared is your variance, right? That means expected value of y squared is sigma squared. Fine. Okay with this?
Yes, sir.
Okay. Now, if I shift it, right? For example, if you take u and shift w by mu, right? What do you get? It turns out fu of u will be 1 by, of course, let's assume that w is Gaussian, 0 mean, okay, let me not write it as w, let me write it as y variance sigma squared, right? So this will be 1 by root 2 pi sigma, right? E to the power or exponential of minus u minus mu whole squared by 2 sigma squared. What is mu called? Mean, right? So expected value of u will be mu, right? Okay, is this fine? It's quite simple, right?
Yes,
So
sir.
scaling will scale the variance or uncertainty. So if you plot this graph, right, this graph with the some sigma, what happens is it will widen. So for example, if you have this for sigma, then 1, then for sigma square it will be some widened. Of course, this will go down here. It will be something like this. Okay, fine. Okay, now let's move on. Okay, so now what can you say about the moment generating function? So what is moment generating function of a Gaussian random variable? This is nothing but expected value of, these are something that we have already
ZR.
looked at. Yeah, ZR, right? So we have seen this, right? What is this? It's exponential of r squared sigma squared by 2. Okay, well, when you say z has 0 mean. Okay, is that fine? So this is, z is Gaussian 0 mean variance sigma squared. So you have this. Is that fine? So if it is of mean mu, what is the answer? Well, all that I can do is I can call that random variable as z plus mu, right? Z is 0 mean, I'll add a mu to it. I get the required. So e power r mu expected value is e power r mu. So I can pull that out. So there'll be a mu. Okay, so g of, let's say, z of r is e to the power r mu times exponential of r squared sigma squared by 2 if this is Gaussian with mean mu and variance sigma squared. Okay, this is something that you need to remember. Fine, and from that you can calculate all the higher order moments. Okay, so I'll write that as a, leave that as an exercise. Find all the moments. Find kth moment of Gaussian 0 mean variance sigma square. Okay, can you do that?
Yes, sir.
Very simple, right?
Yes, sir.
This is about Gaussian random variable, which we were kind of familiar with. Now, let's look at Gaussian random vector. Okay. Gaussian random vector. Okay. So what is Gaussian random vector? So it's kind of this. So we say that, for example, vector. So let me okay. We will. I'll basically talk about this in greater detail, but we say that. Okay. How do I put it? So, do I need to do it formally? Okay, I'll do that. We say that x defined as x1, x2, etc., xn belonging to Rn, a Gaussian random vector. Okay, so RV for short, random vector with zero mean and identity, or let me call this as identity covariance, n cross n covariance. Okay, that is expected value of x is a column vector. Okay, I'll call the x as the transpose of this. This will be x times x transpose is identity. Okay. If you look at the joint distribution of this x of x1, see this small x1, x2 are also these are scalars. So this will be what? It will be 1 by 2 power pi power n by 2. This is IID, right? So that's what it says. E to the exponential of minus 1 by 2 summation I equal to 1 to n xi squared. Okay, so this is the point. Is that fine? Any questions so far?
So here each XAR in 0, 1
No.
means
Xi
Gaussian.
can be anything, minus infinity to infinity.
No, sir, the capital, the random variable you are choosing the Gaussian 0, 1, no, sir?
Zero identity,
X1.
not 1. X1 will be 0, 1. Yes, you are right.
Yeah,
It
X1,
turns out
X2.
that X1 is 0, 1, X2 is 0, 1, X3 is 0, 1, and so on. Xn is 0, 1, and they're all independent, corresponds to this.
So it is something like, sir, a joint PDF of this
Exactly.
X1, X2
So
dot
the
Xn. No, sir?
joint PDF of this is the product PDF,
Yeah.
which turns out to be this. Okay. Very trivial is something that I have written. Okay.
Okay, sir.
Right?
Sir, it's a process, no, sir? Stochastic process.
Well, we don't call it a stochastic process. Okay. We
Why?
call it as a random vector. If you want, you can call it as a stochastic process, but typically when you say stochastic process, you will sort of continue with, you won't stop at n. Okay.
Okay, sir.
Right. Okay, so this is more of a nomenclature. So we don't call this, we deal with this as a vector rather than random vector rather than a random process. Okay.
Sir, as Poisson was continuous, here is this any notion of continuous or discrete anything?
Yes, this is Gaussian, right? It's continuous. What is continuous? What is your, can you be more specific?
Sir, my question is like, sir, in Poisson, there was also interval times there that they were random, independent IID random
There
variables,
is no,
x1,
there is
x2,
no,
x3, like that. Is it
that is
also
exponential.
that kind
Yes.
of x1, x2, xn?
You can think of it like that, but that doesn't lead to anything useful in practice, right?
Yes, sir.
Yeah, x1 could be 0.3, x2 could be minus 58. What will you do?
Okay.
You go from 0.3 to minus 58? It doesn't serve any purpose, right? So, but whereas this can be thought of as, for example, if you have a multiple antenna, since you are looking at Wi-Fi, right? Suppose you have 3 antennas and correspondingly 3 RF chains. There are 3 noises, okay? X1, X2, X3. I call it as X1, X2, X3. You can think of x1, x2, x3 as jointly Gaussian. I'm going to talk about that now. Jointly Gaussian with certain mean and covariance. Typically mean to be 0 and certain covariance. Okay, need not be identity. Is that fine? That's
Sir,
where it's useful.
sir, that I understand. Sir, my question is like when x1, x2, x3 or all these xn's, they represent something with a Gaussian distribution or like that. So then
Correct.
why are we combining all those into a single x, capital X?
That's because it could be jointly, it could be correlated, right? X1, x2, x3 could be
Achha,
correlated.
okay.
How do you write the joint distribution of x1, x2, x3? Right? If it is IID, then you don't even need to talk about all this, right? So it's everything is independent product. But because it's not IID, we talk about all this. But there is another problem. The problem is, of course, you might ask, for example, it's not why only Gaussian, right? Why not consider, for example, jointly exponential distribution, right? One can ask that question, right? The answer is there are two reasons. First, why do you want to look at that? I mean, there are no practical application where you have to look at some jointly exponential, at least very well or repeatedly occurring problems wherein you want to look at such things. So people don't do that. The second thing is characterizing. So how do you characterize a joint exponential distribution? It's very, very complicated, right? Whereas jointly Gaussian, you can represent it in a very nice, cute form. So that's that's another reason, and it's also tractable, and many of the things can be modeled as jointly Gaussian. So I think there are three reasons. Is that fine?
Yes, sir.
Okay. So let's look at what do you mean by MGF of. Okay, this is about jointly Gaussian random vector with zero mean and identity covariance. Okay, it's not for anything. I'm not generalizing it to anything. Okay, so suppose I take a Gaussian random vector. Okay, I want to find I want to find the MGF of W. Okay, so or MGF of X. This I will write it as zero mean. Note that zero is a vector. Okay, vector of dimension n, and identity covariance, that is expected value of XX transpose. This then Gx of R is what? How do you define this? This is, see, if you look at the other things, it's expected value of Rx, right? Rz. Now I cannot do that, right? So Rz, I mean, if I just look at one scalar R and Z or X as a vector, it doesn't make sense. So a generalization would be this, right? See, since this is IID, I can write it as product. Product, I can write it as E power R transpose X. R is also a vector now. Okay, so this R is R1, R2, etc. Rn.
So which are IIDs?
For example, X are IIDs, right? X1, X2, X3, Xn. The X is a vector.
That means that the components are IIDs. I don't understand.
Yes. X1, X2, X3 are IID.
So it can be correlated also.
It can be correlated also, but I'm starting with the simple case, which is IID. Okay, we will see why this is IID. Well, it's a product, right? So therefore it is IID.
Yes. Okay, sir.
Okay. Now, what will be the answer? The answer is also easy, right? It will be product. So this will be product of expected value of e to the power Ri xi. Do you agree? This is nothing but product of MGF of each xi. But all of them are IID, so it's nothing but MGF of one of them. What is the MGF of? So basically, I can write this as product of I equal to 1 to n. What is expected value of Ri xi? It's e to the power Ri squared by 2. Do you agree? Do you agree with this? Because that's what we saw, right? Expected value of the moment. Somewhere here, right? Where was that? Not here. Here. right? Expected value of e to the rz is e to the power r square sigma square by 2. If sigma is identity, I mean 1, then it's e to the power r square by 2. So this I can write it as exponential of minus e to the power minus, okay, product of exponential is the sum, right? Okay, this is nothing but I can write it as e to the power minus ri squared is nothing but what? It's the norm squared, right? Or nothing but r transpose r divided by 2. Fine. Is that okay?
Yes, sir.
Is that fine? Okay.
Yes, sir.
So this is how you compute, for example, the MGF. And similarly, you can compute what is known as characteristic function. It will be something like e power minus theta transpose theta by 2. Same thing. Okay. Now, we talked about IID Gaussian. We talked about random vector, but the specific case, right? IID. Let's talk about what is jointly Gaussian. Okay. So let's look at the definition. We say x1, x2, etc., xn is jointly Gaussian. See, how do you define jointly Gaussian? Any idea? Anyone? Yes. So given the information that, or given the knowledge that we have, how do you define jointly Gaussian?
Its joint PDF is Gaussian.
We don't know what is joint PDF, right? What do you mean by joint PDF being Gaussian? Let's say you were to discover or invent joint Gaussianity and all that. What is the natural thing that you would do? You know how to define a Gaussian random variable, right? But you don't know how to define a Gaussian random vector. What is the process? I think I had told you some story about doctor, right? What mathematicians do? Doctor?
Another problem.
Yeah, right. So you know how to define Gaussian random variables. You don't know how to define Gaussian vector. What do you do? What do you do?
Convert vector into variable.
Jointly Gaussian, I'll just add one more simple thing with zero mean. Okay. Okay. What do? You have to convert that into a Gaussian random variable or a single number, right? Not vector. If I'll convert this, okay. So how do I convert? I'll take, for example, let's say xi, okay. So the ith one xi, sorry, if I construct the following, okay, yi, which is defined as some AIL XL is Gaussian for any AI1, AI2, etc., AIN belonging to Rn. Okay, so of course this is L equal to 1 to n here, and you take any I, okay, it doesn't matter, I equal to 1, 2, etc. Is this fine? You take any linear combination of these, the resulting random variable should be Gaussian. Is that fine? Yes. Yes.
No, sir, I didn't get it, sir.
Okay,
Hello, sir?
so what I am saying is, if you take the vector, okay, so let me, if you are confused with the notation, so let me just write it. I'm just simplifying this, okay. So AI is, okay, is Gaussian for any Okay, is that fine? That means I take any combinations, right, of x1 through xn, the resulting random variable is Gaussian.
Sir,
Okay.
it's AL, no, sir.
This is AL. Yes, you are right. Good. Okay. Is that fine? You
Sir,
take linear combinations for okay, I'll give you numbers a1 through n. Okay, think of it as a game.
So,
Okay.
sir, initially we have done, sir, suppose we have two random variable x1, x2, and then we have assumed z is equal to x1 plus x2. Then there we have find the joint distribution
Correct.
of x1, x2 by using the
Correct.
convolution only, sir.
Correct.
So there we have chosen the a1, a2
So
only 1, 1.
you hold on. So you do convolution when?
independent.
If x1 and x2 are independent, then only you do that. Right? If I say it's not independent, I have to tell what is the joint distribution. That's the whole problem. So how do you characterize joint distribution of a Gaussian random variables is the question now, right? We don't know how to do that. So the starting point is I should first define what do you mean by Gaussian. For random variables, I know because I know the PDF. For joint, I don't know, right? x1, x2, x3, x4, I don't know. So the starting point is this. I'll define what is known as jointly Gaussian. I'm saying we say that x1 through xn is jointly Gaussian. If you take any linear combination, the resulting random variable is a Gaussian random variable. Okay. Of course, is Gaussian with the zero mean. Okay.
So this statement is kind of central limit theorem, like
Not
adding.
really, right? So why do you say this is central limit theorem? It's already. So what is central limit theorem? I think you should understand that. It talks about the distribution, right? Am I talking about distribution? It's exact, right? Y is equal to.
Yes, sir. Yes. Sir.
And this is a definition. Nothing, no limit, nothing, right?
Okay, sir. Yes.
Is that fine? Okay.
So actually, we are, sir, here. We are interested in finding the joint distribution of the Gaussian random vectors, no, sir, directly.
Yes.
Yeah, actually, initially we know the distribution of x1, x2 separately.
Correct. Correct.
Yeah, so we are finding the linear combination of that will be again a random vector. Sorry, random variable.
Right?
Yeah, if we, yeah, sir, I got it, sir.
No. We don't know what to do. Okay. The first step is I have to.
Yeah, sir. Just
join this. I want to define jointly Gaussian. I have no clue of what do you mean by jointly Gaussian. What is it that I will do? The first thing that I do is I'll say, well, I'll convert this into a random variable. How do I do that? Linear combination, fixed linear combination, so non-random linear combinations. If I do that, the resulting random variable is Gaussian, no matter what the combination is. Then I define that the x1 through xn is jointly Gaussian. Okay.
yes, sir.
Yeah, this is the definition. Okay. Now, of course, I know that if x1 through xn are IID Gaussian, right? Then they are jointly Gaussian, and I also know what is the joint distribution, which is this, right? So already given here. Okay. But I don't know what to do with general. So let's try to characterize that in a systematic way. Okay. So now I know that this is the definition of a linear jointly Gaussian. Okay. So what can you say about this? Let X is jointly Gaussian. Okay, I'll give this as homework. Is jointly Gaussian. Of course, zero mean. Okay. And I'll take a matrix A, which is Rn cross n. Then, what can you say about this Ax? Is also jointly, I want you to prove this, okay? Gaussian with zero mean. Okay? I want you to prove this. Okay? Can you prove this?
So by
What do you do
using the definition given above, right?
How do you use that definition?
So, I mean, this is the more general.
You have to use the definition on y. Okay, y is nothing but y1 through yn. You should take any linear combination of that and show that that is Gaussian. So linear combination of y is a linear combination of a and a combination of x, right? So essentially you have to prove that that is also a linear combination of x, right? A linear combination of y is same as linear combination of x. That's what you need to prove. If you prove that, then y is also jointly Gaussian because x is jointly Gaussian. Fine?
Yes, sir.
Okay, I want you to formally prove this. In the next class, we'll continue with this and we'll characterize the joint distribution and we'll look at some properties of the PDF, conditional PDF and all that, the properties of covariance. And then next week we will look at Gaussian process, okay, which is very, very interesting and important. Okay, once we do that, then we will, I think I'll complete that and then we will look at Markov. Okay, hopefully in 2 weeks we will finish this and go to Markov. November sometime we'll start Markov. We will concentrate on Markov for the remaining, whatever course. 2 weeks of Gaussianity. So I would say just start recollecting basic linear algebra, matrix theory, as well as some for engineers recollect Fourier transform, Fourier series, these kind of things. For Sumit, you just look at Hilbert spaces. Okay, we are going to use some notions there, but it will be pitched at a level that all of you understand. Okay. Okay. Any questions? Ayush?
No,
no questions?
yes,
Okay. Praveen, Jayant. Jayant,
Hello,
go
sir.
ahead. Yes. Sumit.
Yes, sir. Actually, why we are interested in random vectors, sir? Because in a Poisson process, we have only talked about the directly we have talked about the processes.
Yes. So even here we will look at what is a Gaussian. What do you mean by a Gaussian process? But before that, we will talk about Gaussian random vectors. There is a reason. Okay. So for example, in wireless communication, right? You have seen routers, right? Wi-Fi routers.
Yes, sir.
There are 4 antennas. I don't know, 4 or 2, depending on which router you have.
Yeah, I have 2, sir.
Okay, you have 2, right?
Yeah.
Each antenna will pick a signal and there will be a noise at the receiver because of it will heat up and there will be thermal noise. Okay, 2 antennas. You agree? So
Okay,
if you look at you can model that noise as Gaussian. Okay, one Gaussian, and you will be sampling. Okay, you will be taking those samples at each time. So these samples are Gaussian random variable. One for the first antenna, the other one for the second antenna. So x1 comma x2 is a random vector, right? And they are not independent in many cases because if the first antenna, whatever circuitry corresponding to that heats up, the second will also heat up, right? Because they are very close. So
Yes.
the noise are correlated. Now, how do you model that? I need that, right?
Okay,
There
sir.
are several other reasons, okay, so which is not so straightforward. This is one straightforward reason why you want to study Gaussian vectors. Jayant?
No, sir. See, I wanted to ask the same question, sir. Why we need Gaussian?
Okay. Okay. I hope you understood, right?
Yes, sir.
Okay. Rishabh? Nitish?
Yes, sir. Yes.
You have any questions?
Next lecture.
Huh? Monday. Oh, no, sorry. We are supposed to have it tomorrow, right? Hello?
So tomorrow we have tests, sir.
Okay, so we will have it on Monday then, next class. So next Saturday sometime, so we have to compensate for one of the classes, right? One of the class. So I'll do that next week. We will have the class on Monday then. Is that fine?
Yes, sir.
Okay, everyone
Yes, sir.
seems to agree. Okay.
Yes, sir.
Nitish, you have
Yes,
any
sir.
questions?
No, sir.
Okay. Okay, then I'll stop here and then we will meet on Monday. Okay.
Okay, sir.